onto the board. All right, so a function f is called differentiable. At x equal to a if f prime of a exists. All right, so let's take a look at an example. And the example I'd like to look at is y is equal to the absolute value of x. So when I sketch a picture of y equals the absolute value of x, it's a v, and I've got a corner right at the origin. Now, the absolute value of x is really a piecewise defined function. On the right-hand branch over here, this right-hand branch is y equals x, whereas the left-hand branch is y equals negative x. And so if I try to draw a picture of the derivative, y equals f prime of x, now I'm going to ignore right at x equals 0 for a second and just look at the right-hand branch of my function. On this right-hand branch, that branch is described by y equals x. So what is the slope of that branch?
Increasing.
Well, the slope is actually constant. The function itself, f, is increasing, but the slope is constant. What is the value of that slope? Yeah, so it's a straight line with slope 1, which means that on my derivative graph, not counting x equals 0, but everything larger than x equals 0, f prime of x is equal to 1. Now, in the left-hand branch of this absolute value, y equals negative x, the slope there is equal to negative 1. And so for every x value up to but not including x equal to 0, our slope is negative 1, which means that my derivative function, f prime, is a horizontal line at y is equal to negative 1. Now that's kind of weird, because this derivative function is suddenly not continuous, and not only that, but I haven't even filled in a hole for this corner right here. And so the question on this corner is, well, what should the value be when x is equal to 0? Should our slope be positive 1? Should our slope be negative 1?
0.
Well, should it be 0? It's not really clear. Let's talk about 0. So at x equal to 0, f prime of 0 will be the limit as h goes to 0 of f of 0 plus h minus f of 0 over h. And so we're calculating the slopes of, so what is this doing? This is saying, okay, if we want to calculate this, we need to calculate this limit. So how do we do that? Well, we start by putting a point here. Here's our point that we're interested in. And I pick a second point. And I draw the secant line between those 2 points. Now that second point, as h, the distance between these 2 points on the x-axis, as h goes to 0, the second point is sliding down toward the point that we're interested in. Now from the right side, what's happening with the slope of that secant line? Slope is always 1. Now remember that limits must be a limit as h approaches 0 from both the right and the left side. So if I instead pick a point, that's green, instead pick a point on the left side. Now, as that second point moves toward our fixed point, our slope is -1. So as we approach x equal to 0 from the right side, our slope is approaching 1, and as we approach 0 from the left side, our slope is approaching -1. Since our limits don't match from the left and the right side, limit does not exist, which means that we have to leave these as open circles. So the limit from left and right do not match. So f prime of 0 does not exist. All right, so here's an example of a function, y equals the absolute value of x, that is not differentiable when x is equal to 0. All right, so that's a little bit distressing, okay? Because that function's kind of cool, right? I mean, y equals absolute value of x. It's a continuous function. There are no holes in the original function f. The only thing that's going on here is that we have this corner right here. So a rule of thumb, sort of conceptual idea, is that when we have a differentiable function is considered a smooth function. And if your function has things like corners or cusps in them, then the function is not differentiable at that corner or at that cusp. So let's make that a little bit more precise. How can a function f fail to be differentiable? Well, a function f can fail to be differentiable if it has something pointy in it. So, for example, here, a function fails to be differentiable at the cusp. Another place where a function can fail to be differentiable is if the function itself is not continuous. So automatically, if a function f is not continuous, automatically not differentiable. And here's a weird one. Here I've got a function that for just a hair-splitting second, that function gets completely vertical. Not long enough to fail the vertical line test, but for one split second, one point in time, the slope, right here in the middle, right here, that slope is vertical. So if we have a vertical tangent, and at that vertical tangent, function fails to be differentiable. Now, where would you see something like a vertical tangent? An example of that might be y is equal to the cubed root of x. Is an example of a function that has a vertical tangent. Okay, questions or comments? So you want to think in your head, differentiable equals smooth, smooth equals differentiable. Function is differentiable if its derivative exists.
So the whole function is not differentiable, not just at that point.
So that's a good distinction, and I tend to be a little bit lazy about that distinction. So we would say that on all of these, each of these functions are not differentiable at A.
Just at A.
So that is not differentiable at x equal to A on each of these examples. Now, other than at that particular point, then we can say the function is differentiable. But if somebody, if a function jumps out at you from a dark alley and says, here I am, and it looks just like this, you can say, this function is not differentiable, and that's essentially correct. But really what you mean is this function is differentiable everywhere except at x equal to a. Okay, so a theorem to go along with this